All right, so today we're going to be talking about some of the many problems facing space travel. So yeah, there's a lot. Well, yeah, this is a little there. Yeah, okay. Well, you'll see. So wait, I messed up. This is wrong. Let me do. All right. I changed it up on you guys. All right. So we're going to be first talking about like the kind of original problem with space travel, which is the rocket equation. Then we're going to move into more like some of the restrictions on how we actually on interstellar space travel. So yeah, the current problem that's facing like space travel within this solar system is the rocket equation, which is exceedingly famous and you'll see why in a second. So yeah, rocket
What's the
equation
link
is
of
like
the slide in the chat?
what?
The link of the slide in the chat.
Okay. Uh, I'll put it in the Google Classroom.
Okay.
Yeah. All right. So the core of the rocket equation is this bottom thing down here in the picture. So delta, and that is read as delta E equals like V sub E times the natural logarithm of what is M0 over MF. And so this rocket equation was made by a Russian physicist with the last name Tsiolkovsky. And so that is just like important that guy, this is like his contribution to science. And the reason why it's so important is because this guides this little equation right here guides all of space travel and rocketry, because it describes exactly essentially what needs to be done. So why that's important is first of all, it describes the motion of rocket-like vehicles, which just means that it exerts it propels itself by exerting a thrust by expelling a lot of material. So if you think of a rocket, right, it's a big tube and it has a lot of fuel in it, okay? And when it goes up, when the rocket is shot up, it is essentially just like throwing a lot of that fuel out, right? So in order to move itself upward, it's just just expelling, like throwing out all that fuel by igniting it and causing that to have a thrust force. But that because you're throwing all that material downwards through Newton's laws of motion, that means your rocket's going to travel upward. And so that is what a rocket is. It's something that expels fuel directly in order to exert a thrust force to then propel itself. So now let's talk about this, what the variables actually mean. So delta V is delta V is the energy you need to get somewhere, right? So as you'll see in a second in the slide, next slide, what that actually like specifically means, but delta V is the energy you need to which it's called the change of velocity. That's what the delta in math, this little triangle, is change in, and the v is velocity. So change in velocity, which represents the energy you need to do something. The VE is like more or less your energy, the fuel efficiency. Like how efficient is your fuel? Kind of like that. Then the M0 over MF is the ratio of your wet weight and your dry weight. So, which is to say how much your wet weight is your weight with all the fuel in the rocket, and your dry weight is the just no fuel in the rocket at all. So, and the way math works is that Viking, yes. Oh, I cannot hear you. Give me a second. Wait, I should be able to hear you. Oh, that ln are you asking about? Yeah. That just is like a mathematical thing. Don't worry about the ln. That's called the natural logarithm. It's just a math operation on don't worry about it. It's just math. That's not one of the variables. The G0 is just the I and then SP and then the G0. Those are components of that VE, but so that's just like secondary. That's like if you break the equation down further, that's what you get. But what we care about is this first thing. Where it's VE and ln of MO over MF. All right. So yes, MO and MF, wet weight, dry weight, wet weight, all the fuel, dry weight, the rocket minus the fuel, no propellant at all in the rocket. So what you end up being is that delta V, the energy you need to do something, is equivalent to the like kind of fuel efficiency of your rocket and the ratio of your dry and wet weight. So the problem with that is that you can essentially in rocketry, in math, because there's 3 variables, if 2 of those are already chosen, that means the remaining one you can't change at all, right? So let's say, so to get from the surface of the Earth to lunar orbit, you have a set one variable. Not one variable. It's a set value of delta V that you need to get from the surface of the Earth to lunar orbit, or just the orbit of the Earth. Sorry, so that is already one variable down, and you can only choose 2 of them. So, okay, that means we can then if we choose the fuel, what our given fuel that we want, that's a second one. So then all we can change from there, if we have a fuel already chosen, and you don't have many choices with there's not many rocket fuels lying around. It's only a couple choices. And the delta V, the energy you need to get from one place to another, is a set value too. That means you can only change that means the ratio between the dry and wet weight of the rocket is set in stone, and you need the rocket to have that to be able to propel itself and reach the destination that you want. So why is that a problem? Well, the problem is more fuel. This means more weight, and then more weight means more thrust. More thrust means you need more fuel, and more fuel means you have more weight, and having more weight means you need more thrust, and you can see the never-ending cycle there. So the problem is that when you have a ton of fuel, that the fuel is not expelled all at once. It's a gradual change. So if I have 100 units of fuel as I'm going from one place to another, then I need to be able to carry 100 units of fuel. Well, not 100. You need to carry some amount of fuel continuously from here to there. So you're always going to need to be carrying more weight than what the rocket is. So if you can't really. So yeah, so if you want to get a higher delta V, you need to add more thrust, which means you need more fuel, right? And you can see there. So then if you want to achieve higher delta Vs, that means you really need to be selective about what you do, because if you require more thrust to reach that delta V, that means that means your fuel cost is going to go way up, because you have to carry that much more fuel to a certain point. So it's kind of I'm kind of explaining it poorly, but it's essentially you if you as you add more fuel, the amount of thrust you get, like you need to carry that much more fuel, so you need more thrust for that. So it's yeah. Yeah, exactly. It just Justin, it just it's a cycle. So if I want to reach the moon, I need a lot of fuel to get there, but that means that's more weight on my rocket, which means I'm going to need more thrust to carry that much more weight, and that means I'm going to have to get more fuel, which means and that adds more weight. Yeah. Okay. I've repeated that like 3 times, so I think we all get it, at least to some extent. And then here you guys can see just certain delta V's that are needed to reach certain areas. So right, so the surface of the Earth to Earth orbit costs about as much energy as to get from Earth orbit to the surface of Mars. So that's why it's so hard. It's so expensive to get things to the ISS. It's because any additional unit of weight that you add on that's not fuel means that you need more fuel to carry that.
Who funds NASA?
Who funds NASA?
Yeah,
The U.S. government.
yeah, that's what I thought.
Yeah.
I don't think there's any way you're gonna get that much money.
Yeah. So okay. I've been on this side for a little bit. So essentially just what you take away from this is that it's exceedingly expensive to get things from place to place in space, because if you add more fuel, it gets into a cycle that is very hard to escape from. But obviously it's not impossible to escape from, because we've gone to the moon and like gone to the ISS, but it's just like very difficult math to solve. All right. Now that we've talked about the core problem of kind of the rocket equation is kind of the main problem with solar system travel. Now let's talk about interstellar travel, because that's way cooler. So, special relativity, the bane of interstellar travel. So this graph is one of the most important graphs in all of science. It is the graph of time dilation and special relativity. But that is not what the important part. The important part is that if you can see here, so c, by the way, c is the speed of light. And on the y-axis here, on the vertical axis, that's just how much time is getting dilated. But we don't care about that part. We care about this x-axis. And this graph shows like all the speeds that you can achieve. So on the x-axis, on every x value that this graph covers is a speed that you can go. As you can see, this graph shoots up to infinity right before it reaches the speed of light. So this the x value for this graph, this line, it will never reach past this vertical line at labeled C. So what that means is that you can never go faster than the speed of light, because just simply because that's how physics works. And then
Did you like break the laws of physics?
no,
Oh,
yeah, that's not you. It's not like
but like, don't black holes like break the laws of physics?
no, black holes follow the laws of physics.
Oh,
Yeah. Black holes exist because we predicted black holes by using the laws of physics. So, yeah. So physics.
but then what about dark matter and antimatter?
Antimatter is fully within the laws of physics. Dark matter, we don't know. Like it's not that dark matter breaks the laws of physics. Is that like we don't know whether dark matter exists or not?
Oh,
Yeah. Antimatter like follows the laws of physics. Dark matter is just kind of like, yeah, we don't really have an explanation for why this is happening. So like dark matter is why it's happening. That's what dark matter is. White holes. Are you like neutron stars, Justin? I don't think those exist. Interesting. I've never heard of white holes.
wait, what is a white hole?
Let's look it up.
Okay.
That's the opposite of a black hole.
Well, I would assume white.
Oh, regions of space where nothing can enter.
So it's like something that has zero mass that cannot be entered from the outside. Yeah, okay. So it's something that has like negative mass, it looks like. Because so black holes.
Why did it get zoomed in so much?
It got zoomed in so much because I was changing tabs and stuff. So yeah, white holes, I don't think those exist, but maybe they do.
Now I'm just trying to think of stuff that break the laws of physics.
Nothing does, because it's not like jaywalking where like I can just do it. You can't break the laws of physics. All right. So exotic matter. Yeah, okay. Anyway, so what you should take away from this graph is that we can never go the speed of light, let alone faster than the speed of light. And why does that matter? So, okay, travel speed, right? So, first of all,
Isn't the background like the Star Wars hyper thingy?
it is something similar, yes. So,
Hyperspeed?
yes, yes, okay. That so the fastest man-made object that wasn't like propelled by a nuke. There's an interesting story behind that. If we
Wait, there's something that's been propelled by a nuke?
yeah, I'll tell the story if we have time after the presentation.
What?
So the fastest man-made object besides that is Voyager 1, which goes 38,000 miles per hour. If you notice that 40,000 kilometers an hour, which is about 25,000. No, oh yeah, roughly 25,000 miles an hour. So around the same speed, give or take. Like it barely even shows up on the graph. So now, yeah, so we barely make a mark on the graph on like the universal highway. Okay. So we're gonna need some way to we should probably try to get somewhere along this graph that's not right there. So we're very, it's very hard to get going very quickly. And Voyager 1's been in space for decades and is still only going at 38,000 miles an hour, which is fast, but it's not fast in the
Isn't
space.
Voyager 1 like the rocket thingy that's been flying for a long
Yeah,
time?
it's a probe that we sent out.
Wait, what's this? Wait, how many miles per hour is the speed of light?
Oh, it's like 100 million or something. Let me check. Yeah, it's like 6 million, I think. No, wait, plus 8 plus 8. Wait, that is like 6 times 10 to, it has 8 zeros in it. So it's 6 followed by 8 zeros.
600 million?
Yeah, 600 million miles an hour. Oh, wait, okay. Yeah, that's meters per second, Andy, not miles per hour. All right. Anyway, enough of that. So, yes, we do not go very fast, and we need to go very fast because going fast is probably good in space because it's space. So, anyway, but there's still a problem because the universal speed limit, the speed of light, still not very fast. It seems pretty fast. It's not very fast. So what that means is that it's like,
It seems very fast compared to us, but when you compare it to like the size of the universe, it's very slow.
exactly. So the fact that the fastest speed we can achieve is like still not that fast. It means that it's pretty hard to like have a central kind of space command, if you know what I mean. Because it still would take years to get from one place to another, let alone like even if you guys are, let's say you guys were on the nearest star, Proxima Centauri. It's about 4.25 light years away. And I was giving this this thing, like this class. That would mean that you guys would be getting this class in 2025. You guys would be receiving it. So quite a while. It's so it would take 4 years for the information and stuff from this class to reach you guys. So
Do we even have internet there?
let's just hypothetically say you would.
Then how do you get into Zoom meetings like that? That's like someone that's like halfway around the world.
It was just, I mean, okay, the Zoom meeting's halfway around the world because the distances on Earth are negligible. I mean, there still is like a delay, right? So if I wanted to play a video game on servers in China, I would still have a delay of like probably 0.2 seconds or something, 0.1 second. The ping was sort of what it's called is about 200, maybe 300 or something like that. And that just literally means that the light from my computer take all the electricity and light from my internet has to literally, it takes that long to travel from here to China. So it still has a delay, but it's not amazingly noticeable. Then there's just kind of an interesting so yeah, it's hard to have like a central space command when it takes years for information and stuff to travel across space. So, Why'd they make Voyager 2 slower than Voyager 1? They're the same speed, I think. I don't think they're
Can you tell the story
measurably.
about the nukes now?
I will tell the story about the nukes after the presentation.
No, but you're gonna forget them.
No, I won't. Don't worry. You guys will remind me, I'm sure, if I do forget. All right. Then there's an interesting thing in physics is that we don't actually know if the speed of light is the same in both directions. In one direction, it could be instantaneous for all we know. So, but there's literally no way to test it.
Wait, how is there both direct? What does that mean?
Let's just say there's like an XY axis or something. And if you divvied up, guys know Minecraft coordinates, right? So if you divvied up the universe into X, Y, and Z planes, which is like this is a XY plane, so a Z would just be like another thing going that way. Anyway, let's say if it was just along let's light from this hand to this hand, it like going this way. It could be instantaneous going that way, but then be really slow going this way.
Why?
I mean, it just could be doing that.
Why?
There's no way to test it. We don't know. It probably isn't, but we can't 100% know it's not like that.
Okay.
It's just interesting. Like, I don't know. It's kind of weird. Like because there's just no way to test it. So it could be like that. And that's just interesting. I don't know. I just thought that was kind of cool. All right. So one the thing that people bring up as like a solution to this problem of having having the speed of light be the universal speed limit is quantum entanglement. So quantum entanglement is essentially saying like these two particles, their quantum states are entangled, which means that they're reliant on each other, kind of. So if I change the quantum state of this particle, then that would change it of this particle. And it turns out that you can entangle particles over an infinite distance, and the change in quantum state would be instantaneous. So if I changed the quantum state of a particle here in my bedroom to and it was entangled with a particle way in Jupiter, it would still be instantaneous.
Wait, but then that means instantaneous teleportation is possible.
No, it does not.
Well,
That's because
it's possible you'd probably die.
that's because these particles cannot transmit useful information. So this quantum entanglement, yes, the quantum state is instantly changed. However, you can't get any useful information out of that. So no information is gone instantaneously. It's only the quantum states are changed, but that's not information. So there's no way you can transfer information instantaneously. It just is. That's not how the quantum entanglement works. So just in case people were thinking like maybe you could do quantum entanglement, no, you cannot. All right. Then space is pretty big. So the speed thing, kind of you run into some problems. So closest star to the sun, 4.25 light years away. Nearest livable exoplanet, probably about 11 light years away. And that's just the closest ones. So if you were traveling at the speed of light, which, may I remind you, not possible right now. So it would take you 11 years of your life to get to the nearest like livable exoplanet.
Wait,
And I say that. And
what do
I
you
say
mean by exoplanet, livable exoplanet?
When I say livable exoplanet, I mean like an exoplanet that has a surface temperature within the human range of like being able to survive.
What
'Cause
about
there's-
air?
Okay, I didn't count air because we technically don't really have a way of doing that. And there's other
Oh, it'd
problems.
be cool if we
And
could
we
find
can-
another Earth.
No, and we can do other things that we can show, like that we can do other things to ensure that we can live on that planet. But the biggest thing we need is like temperature, probably, and so this is a good temperature for potentially liquid water and stuff. Justin, you age slower. That's not true. Richard, I forget the exact name of it, if I'm gonna be honest. Okay.
So when
wait.
you're born, you could just go to the nearest planet using light, and then you'll be on a different planet with no people, and then you don't have to share water.
I guess that's true.
You would be 11 years old that time and get no education.
But technically, you'd be in light years, so it's not physically possible. So you wouldn't be able to do that.
I mean, okay, light years are just a measure of distance. So if you were traveling at the speed of light, theoretically, yeah, you could do that. But all right, no. Okay, Richard, that's what I'm saying is that okay, the nearest exoplanet is in Proxima Centauri. However, its surface temperature is like negative 200 degrees Celsius. So this exoplanet, that's 11 light years away, its surface temperature is about like negative 60 to like 20 degrees Celsius. And that's like actually you can live there. So Jonathan, technically that's not how that works. If you use yourself as a frame of reference, you're never moving and everything is moving around you. So yeah, time is kind of, but we can't go the speed of light. But yes, as you approach the speed of light, time does pass slower for you, because that is part of special relativity. But I just didn't get into that. But yes, as you move closer, as you travel closer and closer to the speed of light, you do time dilates, and so you move.
So you see everything in slow motion.
But the thing is, you can't reach the speed of light, so it's not possible.
I'm just asking, but would it be in slow motion if you could?
I mean, like, what do you mean? Like, I don't really know how to like the world
Time
around
is
you
slowing.
is slow. Yeah, time is slowing, but like the world around you. You would like there would be many other problems. Like if you traveled the speed of light on Earth, like if you had mass and traveled close to the speed of light on Earth, there would probably be like several nuclear explosions happening behind you at all times. So maybe, I don't know.
You could achieve the world record of 300 years old.
I guess, yeah, if you're traveling the speed of light, you do not experience time, but we can't travel the speed of light, so.
So if you could live infinitely.
No, maybe. I'm not a physicist. I don't know exactly the intricacies of special relativity, considering I'm only a high schooler. So I wish I could tell you, but unfortunately, outside of my breadth of knowledge. All right. So yes, and even then it's like a 20-minute difference between Earth and Mars. So if there's like a crisis on Mars, the distance involved, like Earth couldn't do anything about it. Considering so yeah, space is big and there's a lot of problems with the fact that the speed of light is the universal speed limit. All right. So
Isn't space infinite?
the space, okay, so maybe the observable universe is not infinite, and we can't see outside the observable universe, so maybe it is, maybe it's not.
Okay, why can't we see outside the observable universe?
Because the light from outside the observable universe just has not reached us yet.
Why?
Because the speed of light.
Why?
So the universe is about 13 roughly billion years. Wait, yeah, 13 billion years old. So the light we're receiving from the edge of the observable universe is 13 billion years old.
Yeah.
So we can't see outside of that because the light from those things has not reached us yet.
Why not?
Because the speed of light makes it so because it can't go faster than the speed of light. So the observable universe, its radius is about 13 billion years.
Okay.
Makes the speed of light go faster then.
I wish we could do that.
Put a
but we
nuke
can't.
behind the light.
Impossible.
Yeah, so we that's why like the observable universe, it's technically like expanding, but because the light is reaching us, but it's and also it's expanding for other reasons. But yeah, the light outside of the observable universe simply has not reached us yet because the speed of light is a hard speed limit. Yeah, eventually that will happen, Jonathan. And yeah, Richard. Yeah. So technically, eventually the universe will start expanding faster than the speed of light, and at which point the observable universe will actually start shrinking. So yay. Anyway, let's go zooming through. I'm kind of gonna skip this slide. I was gonna do like a Q&A thing, but we don't have enough time. So all right,
Can you talk about nukes now?
we will talk about nukes after this slide. This is the last slide.
Okay.
All right. So big problem is that humanity develops technology roughly at like an exponential rate. So like 50 years ago, the world was very different than it is now. And 50 years before that, it was even it was the technology was like okay, so yeah. The difference between 1600 and 1800 like AD, like the year 1600 and 1800 is relatively negligible. There's obviously like differences and stuff, but not really. But the difference between 1800 and 2000, the years, 1800 Napoleon, that kind of thing, 2000, like like the modern world. So technology develops exceedingly rapidly, and as it develops even more rapidly. So the line for technological development just goes whoop, and shoots off to infinity. Why that's a problem is that, let's say there's a new ship, and it's going to Proxima Centauri, and it can reach there in 100 years. So, and
That's just not worth it.
Yeah. So we're deciding like, hey, we're going to, and let's say there's cryo sleep or something. So you won't waste those 100 years. You'll just be in like cryo sleep or something for 100 years, and you'll reach Proxima Centauri. But by the time you're there, it may be like in the first 25
You'll probably
years.
die that time too.
Well, let's just
Even
say
if you're
somehow
dead.
you are like there's life support systems that prevent you from aging, and you're in cryo sleep, so you never experience it. And there's you're just on a 100-year ship from here to Proxima Centauri. And
How
you
much
get
rocket
there.
fuel would that take?
What? Just all like not outside of our current discussion.
Don't question it.
Yeah, that's so you have that. So you go from here to Proxima Centauri, 100 years. All right. But then 25 years into your journey, you're still in cryosleep. You're not experiencing this. But 25 years into the journey, technology is developed that cuts that travel time to 50 years. So then we send off a ship, okay, and that ship arrives at Proxima Centauri in 50 years. So it's been 75 years since you left, and there's already a ship at Proxima Centauri. And so they have 25 years to develop a base and a colony and all that. And so by the time you reach Proxima Centauri, there's already human settlement there. So, and it's been there for 25 years. And so it's just simply not worth it to go at almost any point, because the technology, the travel time is going to get cut faster than the travel times are currently. So there's no, you shouldn't like go on a ship, right? Because at any point it could be that we can get there faster and get there before you, and by the time you reach there, all that time you spent was wasted because we already have a colony there.
Now, can you talk about?
And I will talk about nukes now. All right, so the nuke thing, there was a nuclear test in like the 1950s, and it was an underground nuclear test, and they covered the hole that they put the nukes in with a pothole that's like a couple hundred pounds, maybe a couple thousand pounds. And so they detonated the nuke, and they were recording it too. And the pothole cover, the manhole cover, sorry, the manhole cover, was in 2 frames of the entire video. It was the initial starting frame, then they detonated the nuke, and then it was about 3/4 up the frame, and then the next frame of the video, it's gone. So using that to calculate the speed, that manhole cover reached about 150,000 miles an hour. So that is the fastest. That's the fastest man-made object.
How high did it go up?
I forget exactly how high it went, but I just know that it reached one. I bet you could calculate how high. But
I'm pretty sure the manhole cover just went back down, and they must have put a
Yeah.
safety hazard over there.
But yeah, that's the fastest man-made object ever, is a manhole cover in a nuclear test in like the desert of America. 150,000 miles an hour. Keep in mind, the second fastest thing is Voyager 1 at 38,000 miles an hour.
The second fastest thing?
The second fastest thing is Voyager 1.
What's the first fastest thing? Like
I googled it and it was shot into space.
Nice. Yeah. So the first fastest thing is a manhole cover. So interesting.
What was
All
the
right.
first thing in space? Like a manhole cover?
What? No. The first thing in space was not a manhole cover. I'm just saying this is the fastest thing that man-made object. The fastest thing that.
Yeah.
So yeah.
A particle is the first thing in space.
All right. Now let's do the.
It was actually shot into space 2 times.
Nice. Yeah. So it didn't like enter Earth orbit. It got shot into space and then fell back down. All right. We
Really?
only
I
have
thought
10
it
minutes for the
It
Kahoot.
was actually going at 125,000 miles per hour.
Well, sources vary. Some people say it's 150,000. Some people say it's 125,000. And I went with the more, the cooler sounding time. So. All right. Yep. So join up on the Kahoot, by the way. The Kahoot. Do you guys hear the Kahoot music?
Yes.
Oh, strange. I don't hear it. Oh, wait. I know why I don't hear it. I'll try the trance. All right, since due to time constraints, I'm going to start it at 7:52, and we're kind of just going to rocket through it here. So.
Yeah, rocket through.
Exactly.
Never gonna run around and desert you. Rick Astley.
All right, we're starting here. You can join midway through, I'm pretty sure, so if you want to, that option is available to you.
Lagging. Tchaikovsky is a composer.
And
Bach in there.
there's another
Bach is a composer.
So is Tchaikovsky.
Yeah, so is Tchaikovsky. Tchaikovsky.
I put Bach and Tchaikovsky in there. Well, because I put Tchaikovsky in there because it sounds like Tsiolkovsky, so I just thought that'd be funny if somebody clicked it.
Why'd you put Bach though?
And then Bach is another composer, so I just put that in there. Cause
you should have put, since it's so hard to spell, you put something like all the options, like once I made a Kahoot and I put all the options of different spelling and no one can get them right.
That'd be evil.
It was evil, I did it twice.
Oh goodness. Yup, so yeah, it's the energy needed to reach somewhere on the rocket. Nice job. Oh, why it says it should be why does. And I made this a little too quick. That's another typo. Yup, so yep, so the red one I just kinda I don't know, I guess that was to prevent you guys from just like clicking instantaneously as soon as you saw an option that says feedback loop, because that just means like more rockets, not like rather than more fuel. And then it doesn't cause rockets to be inefficient. That would be like a fuel decision kind of thing, not a rocket equation thing. Ooh, I don't know. I don't think I talked about this. Wait, did I?
I doubt you did.
Okay, maybe I did. Either way, let's see if you guys know science trivia. Yep, it's Albert Einstein, his big thing, general and special relativity.
For putting me in 6th place.
Yeah, Bohr did.
Bohr is another mathematician. He was very smart too.
Yeah, exactly. Yep, that's true.
And
He
they
did,
were like kind of friends, but then they started like an argument, I think.
Yep, they did a argument at the I forget the exact name of the conference, but they had an argument about quantum mechanics because Bohr was a huge quantum mechanics guy.
I figured out a pattern, I think.
Wait, what's Mach? Like Mach?
Mach 1 would be the speed of sound.
Can you just skip it now?
Mach
Mach
1 would be
11
the speed of sound. Mach 2 would be 2 times the speed of sound. Mach 3 would be 3
Yeah, how
times.
much Mach is the speed of light?
Many, many Mach.
True. Told you it's true.
Yep. So
You don't
it-
really know it's false.
Yep, exactly. We don't 100% know if it's true or false.
True. No, I actually picked true.
Rip.
I was saying true just to get people to do it, but I did it
Yep.
myself.
I misclicked there.
I mean, at least
think-
I'm still in 4th place. Yay.
Right.
You never said that.
Oh wait.
Wait, JK, you
I
did.
clicked
You
the
did.
wrong one again.
You did.
Rip.
Well, I took the wrong one. Come on, I just read the last part.
Like, isn't Proxima Centauri and like Alpha?
I put
Centauri,
Alpha.
like, kind of.
I put
No.
They're like about the same distance.
Proxima Centauri is a star within Alpha
Wait,
Centauri.
I'm still in 5th place. How?
Yeah, so Alpha Centauri is the name of the system. Proxima Centauri is the star within the system.
Oh, no one gets any points for this, right?
Everybody gets points for it.
Wow, I already quit.
You can click the answer.
Ooh, that's interesting. Even split. Nice. And the Rickroll takes 1, 2, 3 again.